So the first problem is the definition of compact set. So a set K is compact in X if every open cover of K in X has a finite subcover. And okay. Also, second problem is S compact. So the first one is NRX, the neighborhood of X near neighborhood of X. You can say that because this is an open set in R2, so it is not closed and bounded. So by Morel, this is not compact. But okay, you can also say that you can construct a sequence so that all of them are compact. So this is NRX. We can construct a open cover like this. So this is the first one, and this is the second one, and this is the third one. So it will become bigger and bigger, and be very close to the NRX, but will never be itself. So this union will be an open cover of NRX, but it does not have a finite subcover. So is not compact. Also, the second one, empty set. Yes, this is yes because every open cover of empty set has a finite subcover. The third one is X finite in R5. So this is yes because every finite set is a compact set. Or you can buy Morel, something like that.
Okay. Is it valid to for question 1?
Yes.
Say that because the open board is open and the compact sets need to be closed. So
No. Not open does not mean not open does not mean not closed.
but compact sets must be closed. So it is not closed. So it is not compact.
Yes.
You mean the open set is open board is not closed.
In this case, this is not closed, so it is.
Yeah, maybe.
Yeah.
If you say that because open set is open, it's wrong. But if you say because open set is not closed, it's correct.
Yeah. Okay. Yeah, that would work. Also, the third one is if K is compact in Y, it is compact in the X. K is compact in X, then it is compact in Y. So assume K is compact in Y, which is subset in X. So we want to prove K is compact in X. Suppose there is an open cover of K in X that is U alpha. Then we let V alpha equals to V intercept U alpha. Then V alpha will be an open cover of K in Y. So since Y is compact, there exists a finite subcover of K in Y. So back to the U alpha root. Because V alpha 1 is subset of U alpha. So U alpha 1 to U alpha n is a finite subcover of K in X. So K is compact in X. The converse is very similar. Assume K is compact in X. Suppose V alpha is an open cover of K in Y. Then because V alpha is relatively open in Y, there exists U alpha in X. such that V alpha equals U alpha intercept Y, and U alpha is open in X. Then U alpha is an open cover of a K in X. So because X is compact, there exists U alpha 1 to U alpha n, that is finite sum cover of K. Hence, B alpha 1 to B alpha n is a finite sum cover of K in Y, which implies K is compact in Y. Is that okay? The fourth question is that if F closed, K is compact, then F intercept K is compact. So first, we have K is compact. So compact implies closed. So K is closed. So because F is closed, F intercept K is closed. And in a compact set, K. So a closed set in a compact set is compact. So we have F intercept K is compact. Yeah, that's all. The last one, prove K, the union of 0 and 1 over n is compact without using hyperbole, because if you use hyperbole, it is a sudden kill. So also let's first draw a diagram. If this is 0 and this is 1. So the point K will look something like this. Most of them will very close to 0. So if we can choose some set here, then we can contain most of the points. If we choose a open set that covers 0, because it is an open set, it will contains infinite points of the set K. So the set, the points outside the open set will be finite, which is easy to deal with it. So that U alpha be an open cover of K. So there exists G in U alpha such that 0 is in G, and there exists a M sufficient large such that the neighborhood of 0 is in G. So we need to deal with the the point that outside the open set. And Gn is the set such that Gn is contained in U alpha, and 1 over n is in Gn.
Yes, yes.
So if we take the union of G1 and Gn minus 1, so in open sets like this, it will be a finite cover of K. So K is compact. Yeah. Any questions?
None. So next week will be Heinkel Hell, and we will not let you to copy the proof of Heinkel Hell in the most general form, but if we want you to prove it on some interval, you should know how to do it. Any questions? Midterm feedback? No? Then I think the class is dismissed. Bye-bye.